Good morning, everyone. So, whatever the title, long title is, basic problem which challenge which I'm trying to solve is detection of Microcystin-LR in drinking water in a very resource constrained scenarios, in a chain of basically where I can fit the sensor, what are the challenges to fit the sensor, and in which situation it is valid and maybe not valid or we cannot handle it. So those are the main challenges I'm trying to solve. So this is my outline. There will be a introduction, sensing scheme, fabrication, and preliminary results, conclusion. So basically, the cyanobacteria is a photosynthetic organism which is found in water bodies. This is the first organism on Earth which started to do photosynthesis. Before that, there was no photosynthetic property. And even when we see the leaves in trees, the green, so basically evolutionarily the cyanobacteria came inside it and became a chloroplast. So basically, the life today what we see or we live the way, it's because of the cyanobacteria once upon a time started doing photosynthesis. So one organism which has lived for so long, it definitely develops some kind of survival mechanism. So one of the survival mechanism is it releases a toxin. We call it cyanotoxins. So there's many types of cyanotoxin. It can be neurotoxin, it can be hepatotoxin. So in general, ecologically, it is in balance. So it will be there in water body, but it's not very dangerous. But due to the kind of large scale agriculture, and we release very high nutrient chemicals like NPK, enriched chemicals in water bodies through agriculture or factories, it enriches the nutrient content in water bodies. And even with the global warming, it gets more and more sun output. So the concentration of toxin, it increases in water. These toxins are then can be taken by fish. Then the small fish can be taken by bigger fish. So there's a bioamplification. And then the humans, so we then take food, or we can have drinking water. So basically, we are trying to drinking water in this area. So then it can affect our liver or neurotoxin and things. So if we look into the study for the fresh water bodies where we get drinking water, so almost 90%, or in case of Asia, so more than 90 to 80% are microcystin. This is the load of microcystin, the toxin. And Microcystin-LR is the most potent of, it's a heptapeptide. So it's a cyclic heptapeptide. It is the most potent of the toxin. So much so that WHO has put a 1 ppb of limit for drinking water. So anything above of this limit in drinking water, it will be dangerous for humans. So now monitoring and then the management of this is a big challenge. So if I take the case of India, particularly how the monitoring is done. So in India, whenever we are doing testing, there are 3 tests per year minimum has to be done. 3 tests means 2 bacteriological tests. One is pre-monsoon, before the rainy season, and one is post-monsoon. And 1 test is chemical test, like you do BOD or total dissolved solids. That will be pre-monsoon, when the concentration will be higher, because after monsoon, the concentration will become lower, we won't get. So total 3 tests has to be done. Now, the challenge for drinking water is, this is our village administrative system. In the democratic system, so final democratic power in a local level for a village system is, we call it village panchayats. It's a kind of semi-autonomous, you can say semi-republic, village republic. So they have a decision. They basically much testing has to be done, how it has to manage, and what funding, they generally handle those locally. Now, what happens is, if you sample water from here, so those water is sampled and those go to district level. So either village district or go to urban and those districts, those water sample will go. There will have a laboratories. They will test, and those results will come back to village, and then they will take action. Now the action is successful or not, so they will again send back to the laboratory, and they will say success or failure. So there's a back and forth is there. Now we take all of India. So almost the water sources, approximately there are 6 million water sources. And in the 6 million, if we take 3 tests approximately, so 12 to 18 million tests have to be done, minimum. So you can calculate if there is per laboratory, there are 3,000 tests per year it can do, then you can calculate how much laboratory is there. Now, pre-COVID data from government is that approximately 2,000 labs are present in India. And within the 2,000 labs, only 50 are NABL certified, accredited. NABL is National Accreditation Body for Testing, Laboratories and Testing. So what is this? I think in Europe, you have mangoes and basmati rice. So these are basically ISO certified. So whenever something is basically agricultural products going, so it should pass these tests. So these are very advanced labs, but there's only 50. So now these are being used. So it is not possible to test those things. So one of the way it is managed in India is through FTKs. There's field test kits. It's small. You can say a single test kit or a set of 10 test kits. It will come and you can go to village and So what we are doing is we are trying to make a IDE, which is very easy to manufacture, fabricate, and it can be transported and brought back, and at a local level testing can be done. So this is the basic scheme, 3-part. So scheme is very simple. So there will be 3: the fabrication, there's a testing, and in between this is the biofunctionalization. So basically it's a Cysteamine cat, means you get amine groups above it, there's a carbon, and then you do a cross-linker. So you have aldehyde group, you take out the water, so that amine group binds and the specific antibody binds, and then you block the remaining portion with the BSA. So now then you do a testing. So fabrication, so what we are doing is we are using a laser engraver to make our mask. So these laser engraver, if you do proper power adjustment, we can get a 380 kind of and gap of 380 approximately. And if you pass the carbon ink, then you can get a kind of 480 finger width and 289. Obviously, because after you put it, when it settles down, the ink, basically carbon expands a little bit, and then you cure it for 40 degrees for 24 hours. At a time, for an A4 sheet, PET sheet, that is 100 micron PET sheet, you can get squeeze it and get a 90. Add it together, you can get 90. Almost for the 90 sensors, 20 will be lost. You can't get 20, so 70 you will get. And these are thin sensors. So if you have transportation, if you're like a printer bunch, you can send them those one sensor pad above it, thin paper, and bunch it, or you can roll it a little bit. Obviously, the diameter has to be a little big, so you can the space is less, and you can transport this sensor. So this is the upper substrate fabrication. Second is this is gold nanoparticle. There's 25 nanometer gold nanoparticle Cysteamine cap. So this is the same image of bare sensor, this carbon, and this gold nanoparticle has been immobilized. So you can do this packed thing, and this is your mapping data. So now the sensor, and you have amine above it. So these are preliminary, very preliminary results. So these is basically the bindings when you're doing. There's a baseline of DI water, then the glutal and antibody. So now this is for lake water signal. For lake water, what you are doing, that we're taking lake water, we are making a spiking it to 0.1 ppb because our limit is 1 ppb. So in 0.1 ppb, we spike it, and then we syringe filter it fit to 0.2 micrometer syringe filter, so that the bigger particles like bacteria and phytoplanktons that can be removed as it may interfere, and then we are getting a signal. So this is filtered lake water, and above it we are getting a signal that is 0.1 ppb and then 1 ppm. Same we did with basically we took a 6 kilohertz signal because there our standard deviation was less. We also checked with the PBS and lake water, so getting good result. Now transportation and storage. If we store it for what you can 4 degree, if you can manage a 4 degree, we call it antibody. Then for 5 weeks we are getting a kind of 90%. It decreases, but obviously we have to store it for 4 degree. Means there has to have a facility of fridge maybe, or maybe cold storage, vegetables cold storage that can be used. So the main preliminary target that lake water matrix, and before we can detect as low as 0.1 microgram, that is 1.1 ppb. 1 month we can store if we can manage 4 degree. Obviously, cross-sensitive studies and other studies has to be done. But this is one part. If we are solving this sensing problem, but what about the other part, the device part? Because mostly the devices we are using Autolab, so we have to make a device. So this is we working on. This should be very low maintenance, and very easily it can be opened up and it can be maintained locally. So we are looking into cartridge, which is very simple cartridge, low maintenance. So we are working on it, and this is basically how to collect water from lake, and if it can on-field testing can be done. So these are my Minister of Education. So I'm getting my scholarship from here, IIT Bombay. This is my lab. That is Biosensors and Bioinstrumentation Lab. It's in Biosensor Bioengineering Department for IIT Bombay. The Ministry of Science and Technology is also providing me funding. Thank you.